episode 8.8. So today we're going to be talking about motion with air resistance. So currently we're going to look at x, motion in the x direction. So horizontal motion for now. And let me finish trying this. So I'm not going to be using some sphere approximation. We're only going to be considering this FV, and we're only going to be considering, for now, we're going to look at linear motion. Okay, we're going to look at linear motion for now. So let us think about what we need to do. So first things first, we have a diagram of our situation. And next thing we want to do, we're using Newtonian mechanics. Let's do F equals ma, right? And so we know that this is the F net. Sorry, we know this is the sum of forces. We only have one force, and that's this FV v hat. So we are only considering a linear motion. So this is going to be negative bv, right? Or probably better I write it an x dot, right? So what is this? We have this mx equals negative b x dot, and I'm actually going to remove these arrows because I technically do not need them right now. And they only make things a bit harder to see. So I'm going to use this simplification. So I'm going to use thing tau equals m over b, and I'm basically going to divide it by m on both sides. So we get x double dot equals negative x dot over tau. And what is this? Well, this is a second order, if you remember from linear equations or differential equations, this is a second order linear ordinary differential equation. So we have not looked at how to solve these, but we can technically treat this as a first order in x dot, which is exactly what we're going to do. So this is not a very difficult differential equation to solve. In fact, this is one of the simplest. This is, v dot equals minus a v, right? So we solve for v. What are we going to get? This is the exponential function. So we get x dot is equal to x naught e to the minus t over tau, right? So I actually should probably explain this x naught. So the way we're going to be differentiating this is going to be from t0 x double dot over x dot, and then we're going to say these are functions of some s ds. We're using the fundamental theorem of calculus here. This becomes x dot t minus x dot 0. And I'm going to call this x dot 0. I'm going to call that v naught, right? And we obviously do the same for both sides, but since this is just a constant, then that just we just add a t to that. So what happens? So we have x dot equals v naught e to the negative t over tau as our solution. And well, we would just want to differentiate this once more. So we do the same thing, integral t over 0 s ds. And what do we get? So we're going to get x minus x naught is going to be equal to v naught as a constant, And we're going to have this integral from t over 0 e to the minus t over or s for tau ds. And what that's going to give us is, v naught. So v naught e minus t over tau negative tau v, sorry. I'm going to clean that up. Negative tau v naught e to negative t over tau, or negative s over tau from t to 0. And what happens when we expand this? This becomes negative t v naught e to the t over tau, or negative e to the tau, plus tau v naught e to the 0. And we can move this around. We get tau v naught 1 minus e to the minus t over tau as our solution. So that's our equation. So our two equations that I want to look at here. First one is this x dot equals v naught e to the minus t over tau. And the second equation is x is equal to x naught plus tau v naught 1 minus e to the minus t over tau. And these are the equation. This is the equation of motion when we consider drag. So let's actually graph these. So let's think of this first graph. Here's our t. Here's our v. What's this look like? So it's going to be v naught. When t is equal to 0. When t equals 0, x dot equals our initial velocity, right? So that makes sense. But as t approaches infinity, what happens? Well, this approaches e to the negative infinity, right? Which approaches 0. Very, very simple limit analysis. And so what does this graph look like? It's going to look like this, right? And this is going to be infinity, and it's going to be 0. So there's some interesting points I want to highlight on this map. First one is tau, 2 tau, and 3 tau. And so why am I highlighting these? Because when t is equal to tau, we have e to the minus 1. And e to the minus 1 is important because that is actually equal to 63%. And so you can actually test this. Do e minus e to the minus 1, right? That should get you that. And so e to the negative 1 means that we've 63%. We've decayed by 63%. That's what that means. So 63% of the velocity is gone. Right? And likewise, e to the negative 2 is about 86%. And e to the negative 3 is about 95%. So as you notice, as we move through this, we have 86%. And here in red, we have 95% decay after 3 tau time has passed. And then once again, remember tau is equal to this coefficient is equal to mass over the coefficient of air resistance, right? Now, what's next? Let's examine this graph, the actual graph of motion. So, what's that one going to look like? Kind of similar. Here's our x. And I'm going to start with x naught here. So at time 0, we have, that's about what happens. So when t equals 0, we have 1 minus 1, which is 0. Okay, good. Right, so then x equals x naught. So that makes sense. But then what happens as time as t approaches infinity. What is the limit? The limit as time approaches infinity of x is limit as t approaches infinity of 1 minus or x naught plus tau v naught 1 minus e minus t over tau, right? This is going to be minus infinity, right? That turns into 0. So we end up, this is equal to x naught plus t v naught, right? 1 minus 0. Or just x naught plus t v naught. And if we take away this, so this is the maximum, our highest possible value. I'm going to call it x infinity, right? This is so our distance that we travel is going to approach this value asymptotically as t approaches, infinity. And one more thing to mention is that this distance, right, this, I'm going to pick a better color that I haven't used before. So let me write that there. This distance here is equal to tau v naught. So it will travel. So if we ignore its initial position, cart will travel at most t v naught meters, or m over b v naught. Okay. And that's it for horizontal linear motion. It took us about 12 minutes, but hopefully that made sense. Next, we're going to actually consider vertical motion, where we're going to have to consider gravity.